So we want to talk about polar moment of inertia. And so the polar moment of inertia is kind of like a area property. So it's the cross-sectional area. It's a property of this cross-sectional area. So as I twist it, right, there is some resistance that's inherent to the geometry of this cross-section. And it's that resistance that we refer to as the polar moment of inertia. Much like the moment of inertia, I, for a beam, or for any cross-section is really its resistance to how well it resists bending. The polar moment of inertia is how well the object resists twist. And so if you could imagine I have two noodles, one that had this shape and one that was much larger, which one would you expect to twist more? I think you'd expect the smaller one to twist more, and you'd be right because it has like less area, so it has less lower polar moment of inertia. And so we'll derive the equation for polar moment of inertia. We'll even do it, as you can see, our noodle here is hollow. So we'll do it for a case where we have a hollow section. But just remember, if you don't have a hollow section, just use the inner radius equals 0, and you'll be able to use the same formula. So let's go ahead and do a little calculus, and we'll have the polar moment of inertia equation in no time. I know area integrals can be a little bit intimidating, but I don't want you to be intimidated by this. We're going to go through and calculate J. So remember, J is the area integral of rho squared dA. Now once we do this, we'll have a formula that we'll be able to use for all circular rods. So we won't have to do this area integral each time. But it's good to know where the formula originates from. So in doing this area integral, I want you to recall that dA equals dx dy in a rectangular coordinate system. But I want to work in polar coordinate systems because this is a circle. So dx dy translates to rho d theta when we look at polar coordinates. And you can go back to calculus 2 and recall how this happens. But for now, just take my word for it. So J is going to be the area integral of now rho cubed d rho d theta. All right, and so how do we perform the calculations of the area integral? Well, I have two variables to integrate with respect to, so I'm just going to turn this into a double integral. So I need to integrate with respect to rho. Now rho is going to vary in this case from my inner radius to my outer radius. And so those will be my bounds on my integral. So that's my bounds for rho. Now my bounds on theta is going to be the entire circle, which goes from 0 to 2 pi. So my second integral there is 0 to 2 pi, and that's with respect to theta. So I need to move d theta to the inside integral, and I'll move d rho to the outer integral. All right, so now it's just some calculus to do the appropriate integrations here. Now I don't have any thetas in my function, and so when I integrate the inside integral, this is going to result in rho cubed times theta. And now I have to evaluate this from 0 to 2 pi. So I'll put my brackets there to indicate that I'm evaluating from 0 to 2 pi, and I keep my d rho on the outside. So I plug in 2 pi, and then I plug in 0, so I do 2 pi rho cubed minus 0. So this is going to give me the integral from the inside radius to the outside radius of rho cubed times 2 pi d rho. Now I do my calculus, integrate rho cubed with respect to rho. This is going to give me rho to the 4th over 4. And then my 2 pi remains a constant. And now I need to evaluate this from the inside radius to the outside radius. So this gives me my final formula for J. J is going to be pi over 2 times the outer radius to the 4th minus the inner radius to the 4th. And I just want to point out to you, make sure we follow our mathematical rules for exponents. So the most common mistake is that students will take the outer radius minus the inner radius and then raise it to the 4th power. That's not this equation. This equation has you taking the outer radius to the 4th and then subtracting the inner radius to the 4th and then taking all of that times pi over 2. Alright, I think you'll be able to calculate J pretty easily, and I look forward to using it in some engineering calculations.